Hello, to Darkness344 here, and in today's video we'll be covering simplifying Boolean algebra. So this is quite important skill to learn, I guess, and it will help you compacting down your circuits, making them a bit more simpler. So I'll be running through a couple examples and stuff. There's no like exact formula or way how to do it. It's kind of up to you how you simplify down expressions, because there's many ways to do it. But hopefully this video will help you see some like patterns and techniques, because if you simplify down your algebra, you will of course get a much more simple circuit. So yeah, with that, let's just get into the video. So this video will just kind of demonstrate a few different examples you might find. When it really comes down to it, you'll probably be only simplifying your own circuits, so these are just kind of like random examples, but they should show a few different techniques and stuff, and hopefully they'll help out a bit. So of course, when it comes to any of these problems, you have to of course remember all the Boolean identities, because if you don't know them or you miss one or two of them, you might miss a way to simplify down your circuit, which could result in not getting the actual simplest form of the circuit, or the expression even, but you'd of course probably turn the expression into a circuit later on. So here we just have a very simple expression over here. Q equals not A and B and not C, or not A and B and C. So of course the not A and B and not C is ORed with these ones over here because they're all in the brackets. So for this example, what we can do is actually look for patterns. So because we only have three terms, there's probably going to be a pattern in it. So, well, over here we have not C, but over here we have C. Well, we have a B in here and a B in here, so that's one common factor already. But then we also have a not A in both of them as well. So that's two common factors. So instead of just taking one common factor out, you might as well just take out them both, because whenever you're doing simplification, if you take out the largest common factor, it's going to be a lot easier than taking out just one, then another. So what we can do is take out not A and B. So if we go not A and B, and then our two factors will be not C or C. So this will be not A and B and C, or, well, not C or C even. So there we go. We've already simplified it down to this a bit, and I'm just going to get rid of these real quick. If you remember, anything ORed with the, well, inverse of itself is always going to be 1. So not C or C will always equal 1. So now if we write this out, we have not A and B and 1. And then of course anything and 1 is just that thing, so we get not A and B. So there we go, that's our answer. Q equals not A and B. So this was just a fairly simple example, just to kind of get familiar with the concept that you can always take out a common factor. So always take out the largest common factor, because it'll just make the simplification a lot easier than taking out a smaller one. For instance, if we just take out, say, not A, we get not A and B and not C, or B and C in the brackets. And then of course we can do that again, so not A, and then we take out B, and then we get C or not C. And then of course we can simplify this down, so we get not A and B and 1, which just goes down to not A and B. But this is a bit more complex than just taking out the B and not A in the first place, because of course it's the largest common factor. You might as well just factorize it out. So now we just got another example. So we have not A and not B, or not A and B. So yeah, we can just take out the common factor, which is not A. So we have not A and not B, or B. And I'm just going to put these in brackets again. So there we go. And then of course this simplifies down to 1, so that's not A and 1. And that of course just simplifies down to not A. So Q equals not A for this example. So this was just another one to show that, well, of course not A being the largest common factor, you just factorize it out. So sometimes factorizing stuff out isn't always the best example. So over here we have a common factor, so we have B in both terms over here. So B here as well as B here. But if you notice, we also have this not B over here, so not B or C. So sometimes it's actually better to expand first, because that can actually lead to simplification. So for instance, of course you can try them both, but for this one I'm just going to try expanding first. So if we have not A and B and not B, or not A and B and C. So of course these would have been from the expansion of not A and B and not B, as well as not A and B and C. And this will just be ORed, so let's just put it like that, with B and C. So now, well, we still have that common factor, not A and B, of course, but we factorized it out, so we might as well try simplify this. So of course we have the B and not B, which simplifies down to 0, so we have A and 0, or not A and B and C, and these would be, we'll just put them in brackets for now. And of course anything and 0 is just 0, so then we have just not A and B and C, and of course the or B and C. Now of course we can always factorize out the B and C, so we get B and C, and then in the brackets we're going to have not A, and then we're going to have or 1, because B and C is the same as B and C and 1. So to get 3 terms, we can just add a 1 in by ANDing a 1 in, and this means we can actually factorize out like this, which just means it's a bit simpler to deal with, because then we have 3 terms on both sides. So now of course not A or 1 is always 1, so now we have B and C or 1, which just leaves us with B and C. So there we go, Q equals B and C. So this example really just shows that sometimes if you expand first, you can lead to a simpler result. We expanded this into this, and it meant that we could factorize it later on with the taking out the B and C, and of course it left us with just B and C as the final result. So this example over here has a lot of bars and stuff and looks quite complex, but in reality it's actually not that hard, and is a perfect example for why you can use De Morgan's theorem to simplify your expression down. So if you can't remember, a few videos ago we covered De Morgan's theorem, and that is where if we have A nor B, this is the same as not A and not B. So you can break the bar and swap the term. So the same thing goes if we have A and B. This is the same as saying not A or not B. So by using these concepts, we can actually split this up a bit, split the bars, and this will allow us to simplify it a bit easier. So the first thing we're going to do is actually just break this bar. So of course we always go that top bar down. So we're just going to have A and not B, and then we'll have a bar over that. And then of course we're going to split the bar, so we'll have a bar over that bar. And this will be or instead of and. Then we have A or not B, and then a bar, 2 bars over that because of this one. And we'll keep the brackets in for now because it'll just be easier to follow. And of course we have or not A and B. Now a couple videos ago we of course went through the Boolean identities, and one of those identities were 2 bars cancel out. So of course if we had not A, this is just the same thing as having A. So we'll just cancel the 2 bars out, so now we have A and not B, or A or not B, because of course we can cancel the bars out, or not A and B. So now what we can do is look for common factors. Well, the first common factor I see is just this not B over here, and then of course we also have an A as well, but let's just try use the not B and take that out. So we have the not B over here, and then in the common, well, inside the brackets we're going to have A. But of course this one isn't actually ANDed with anything. So what we can do of course is just AND it with 1. So we can have A or 1 inside the brackets. So that's taken out this out of the equation, and it's also taken out that. So of course we'll just put the rest in. So or A or not A and B. And of course A or 1 just simplifies down to 1, and not B and 1 of course simplifies down to not B. So we can just have not B here, or A or not A and B. So now if we rewrite this expression a bit, so let's say we have not A and B, or not B, or A. To this we can just use the absorption law. So not A and B or not B, of course just simplifies down to not A or not B. And if you go a few videos back, I showed out how this actually works. The term doesn't just disappear, it does get absorbed. So now once we have this, we still have the or A, but of course not A or A is just 1, so 1 or not B, and 1 or not B of course just goes to 1. So our final output is just 1. So this whole expression over here just simplifies down to 1. So instead of having all these different logic gates and stuff, you could just replace it with a lever, for instance. So sometimes simplifying things down can make the circuit a lot simpler. But yeah, this really kind of just shows how you can use De Morgan's to help simplify things down. Now this one over here is just kind of the final one, and it's quite similar to one of the first ones we've done. However, some of the signs have changed and we've got this additional B over here. So we're just going to do what we originally did, and we're going to expand the brackets out. So we have A and B and not B. And then we also have, or A and B and C, or B and C, or B. So the first thing we're going to do is, well, actually we can just simplify this down over here already. So B and not B, of course, equals 0. So we have A and 0. And of course, A and 0 will just equal 0. So we have 0 or A and B and C, or B and C, or B. Now over here, we can actually factorize two different things. So either we go for the B and C in both these terms over here, or we could go for the B, which is on all three of these terms. So either way, we're going to get the same answer, but I'll just show off both of them. So first of all, well, what happens if we just factorize out the B? So of course, to make them all three times, we're going to have A and B and C, then or B and C and 1, and over here we're just going to have or B and 1 and 1. So now let's factorize out the B. So we have B, and so C and A, and then this one we have C and 1, and then this one we have 1 and 1. Now we can simplify this down a bit further. So if we factorize out the C, we're going to get C and A or 1, or 1 and 1, which is of course just 1. So now we don't even need to simplify this bit down, because of course anything or 1 is always just equal to 1. So we get B or 1, which just goes to B. So for this example, our answer just equals B. Now what happened if we factored out the B and C instead of just the B? So of course we can do that. So B and C, and then in this one we'll have A or the 1, or we're just going to write this as B over here because we won't bother. We can't take out B and C from this one, we can only take out B. So we'll just leave this on the end like that. So now of course this factorizes down to just 1, so we get B and C and 1, or B, which just goes to B and C, or B. So now of course we can just use the absorption law again, and this just goes down to B of course. And of course if we just prove this, we have and 1, and factorize out the B, so B and C, or 1, and then that just equals B. So yeah, two different ways of doing it. This one, factorizing out the larger factor, is a tiny bit easier to follow, but either way works just fine. I'd recommend always going with the largest factor, just because you're less likely to make mistakes, where this one, of course, we have the 1 and 1. We have lots of 1s in this one because we've just added them in. So sometimes it's better to go with the larger factor, because even if it's a tiny bit longer, there's a bit less chance of you making a mistake. So I hope this video helped out a bit. Of course, simplifying isn't for everyone. The next couple of videos, I'll be going over Karnaugh maps, or K-maps, as some people call them. And this is just a slightly easier way to simplify down large expressions. However, you still need the basic simplifying skills, because you need to simplify the result of the K-map as well, because it doesn't always produce the simplest form. It can sometimes get even simpler. But just for like general use and stuff, K-maps are definitely the way to go for simplifying down anything more than like 2 or 3 variable expressions. You want to be using a K-map. It'll just make things a lot easier. So yeah, the next few videos will go over that. Hopefully this video was a help, and I guess please like and subscribe, and I'm out.